Okay, good. The class today is just for working, so fasten your seat belts because you're going to be asked to work in groups to solve two problems. And so at the end, in the cooperative work in this class, it will be asked just to sketch the solution as usual, and with some more professional tool to do. And the idea is that in your homework you can, if you want, to write code for solving the problem in general, as we did before. So first, I will put in our web a workshop, a module that is called workshops, if I remember, in the Moodle terminology, in the Aula web terminology. It is the a sort of repository, and I'm asking you to upload your solutions if you want. We have one solution by Marco Fedotti. I'm watching him. And so I'm asking, and I want you to develop solutions with no evaluation at all. Unfortunately, they cannot be anonymous, but I think it's good to show your name if you write codes, and even multiple solutions for the same problem. So we have a couple of open exercises. The one we discussed it yesterday. The one was the first one we discussed it yesterday was the publish subscribe, or something similar to publish subscribe with multiple shells or multiple windows using the one producer, the process G, producer of information, and three subscribers or pseudo subscribers we have called S1, S2, S3, with the idea of simulating the distribution of items, and including, we have shown how to, the concept of having separate shells to interact with single processes, and using only one structure for file descriptor for distributing information. It was named pipe. So we have sketched, and you have seen, you have analyzed the code I've written to show how to open new shells. So I'm asking you, those of you who want to do this exercise until the end, just to write, to compile, and if they are pretty sure that it works, but it doesn't matter because it will not be evaluated, please upload and let that your work can be useful for other students. So and the second exercise was just the last one we have discussed. So the waiting for a signal and carrying out a computation on the upon receiving a signal. That is a really important topic. So the last two exercises was those two exercises I've just discussed now. Please code them and upload your solution in the workshop subsite of our web that I will open today. Completely freely, no evaluation at all. It's just cooperative work. So just like you were in a group and showing your comrades, which is the possible solution. So you can discuss together all together. So after saying that, let me show you the next exercise I want you to, I propose to you now in class, in groups. Let me share the screen. Is this one, okay. Pseudocode. Can you read this?
Yes, we can see.
You can read. Is in our web. In our web is in Word, Microsoft Word format. The reason is that so you can write on it. The idea is to solve directly on a sheet of paper, on a virtual paper, a solution using pseudocode. What is a pseudocode? We have discussed it yesterday. Well, everybody knows what is it, and everybody has his or her personal style and rules for writing a pseudocode. In general, the idea is that the pseudocode mimics or is very similar to the real code, but avoiding or dropping non-essential parts. So you don't write the prefix includes or data types. It is not necessary to detail data types if not relevant. So, okay, but you must what's right directly the system calls and all statements that are relevant for looping, for reading, writing, and so on. And in this case, obviously, is not necessary to include all error management that in a real code, professional code, is mandatory. So it can be very synthetic, and so the code can capture the idea of the construction of the scheme of the solution. And also in the pseudocode, personally, usually I make some small drawing, childish drawing as ever in that case. So which is what's the problem to solve? A master process is similar to the last one yesterday. So where is the bar? Master process. So that interacts with the shell. So it's interactive. Here is the smiling man interacting. And inputs from terminal to integer value. The integer values are time periods because of the two child processes. So there's child 1 and child 2. They are periodic processes, so they simply loop and do nothing except, for example, writing on terminal some message so that they make us know that they are working. So imagine a loop with the write or with the printf or something similar to that, that periodically C1 and C2 say, I'm alive, I'm working, I'm cycling. The idea is that P is a scheduler for those two processes. So if, for example, the cycles are, for example, 2 seconds or 3 seconds, and this cycle may be 5 seconds or anything you want. The idea is that P, the aim of P is just scheduling them with this cycling time. And this is due dynamically because here it is clear there is a male scientist, but can be a female scientist, decides the value of those cycling times. So it's a rough scheduling system. And the idea is that the P manages the commands, three possible inputs from the user that can change anytime the cycle time of those two children. SN. S says, okay, S stop, and G is go, and you say the number of the process, so the number of the children. So in this case, is not you cannot change. So at the first step, you simply have commands. So stop C1 or go C1. In this case, stop 1 or go 1, or stop 2 and go 2 with fixed cycling time. And a third command just to terminate everything. Everything means to terminate C1, C2, controlling that they are exited successfully and exiting P itself. So this is the first step. The second step, not written here, change DT1 and DT2. Change in the sense that you can add commands. For example, T1, 5 means the period of children 1 is 5 seconds or another value. So, but do it at the second step. First, you must solve the basic problem, how to stop and resume all the processes. There are several possible solutions. You must choose your solution. Refer to the slides on signals, and there is everything inside. I didn't add so far the signal weight that I mentioned yesterday. So a system call to wait for a signal. You don't need that. I will update the slides afterwards. When you go to the second step, not written here, you have to decide two policies. One is the simplest is to communicate C1, C2, for example, using pipes. The value of the cycling time. It's simple. So basically this way, there's no difference between the first solution depicted here and the advanced solution with changed values, those values. The simplest way is doing that. So communicating them, which is the cycling time, so they can change. More efficient solution would be to and the best solution is not communicating to them the cycling value, this value, but just to keep the value internal P and activating C1 and C2 at due time. So having inside. This is a bit complex, probably more complex, but is the real and efficient solution. Doesn't matter. So you have 2 pages, write in groups the solution here in words, and when you will be at home, finish code and finish the exercise and upload on the workshop part. Okay, is it clear to everybody? Hope so. All those exercises are just to make you able to solve exchanging experiences and suggesting each other what to do. I think it's the best way to proceed. We will. I will judge. Well, I will have an idea when you upload your solutions, if you want to. Okay. I make the breakout rooms. If you don't succeed in sharing the screen, because it's a bit tricky, I think I have allowed all you to share the screen. If you don't succeed, push the button and alert me. I will get inside the breakout rooms and I will change the policy for screen sharing, okay? Okay, small rooms. No, not so small. Okay. 20 minutes for doing that. Welcome back. Well, I hope that you succeeded in writing and discussing purposefully a solution. I think it's an interesting exercise, similar to the yesterday's one, but with some new item. I hope that you have also discussed how to solve the further step, as to say, how to change dynamically the cycling time of the 2 processes. And for this, I want to show that in that case, this okay. If the idea is that the process P manages the cycling times of the children, so it is a real scheduler, a centralized scheduler. The simplest simplest system call to use inside the process P, the scheduler, is the alarm system call, in the sense that the process P might wait for an alarm with a minimum delay time, so that at any time the alarm, the SIG alarm, is received by P, it decides to activate or not one of the children, depending on the cycling time of the. For example, if you call the alarm to send back to the process P a SIG alarm signal every every second, the process B might schedule the children with the cycling time multiple of 1 second. Of course, it cannot schedule uh, children with cycling times lower than the value you assign to the alarm. So alarm should be the unit of the quantum of the schedule, of the main scheduler. This is a normal way in which we schedule processes using a centralized scheduler. I want to, what's happening? Okay. So, I told you that I will open a component in Aula Web so that you can upload your solutions, and please upload also pseudocode solutions. So everything you're developing, try to, don't be shy, don't be timid, and upload your solution to share with your colleagues. Well, second work today. The second work as the cooperative work has to do with the theoretical concurrent programming computer science. So I think it's an interesting point. Probably it's the only one theoretical problem I want to show you. I'm asking you to solve using POSIX primitives, and in particular non-determinism and mutual exclusion. And so let's go inside the discussion on the presentation of the problem, a theoretical problem. That is, we can use Wikipedia to do that.
Professor?
Yeah?
Could I ask a question based on the problem that you'd given us?
Yeah.
In the third one, where it says where n is equal to 1 or n is equal to 2, is it to identify the child process, or we just assign that if n is equal to 1, then it should identify child process?
Yeah, well, P has to identify the child processes to decide which is one. If you use signals to wake up and and stop those processes, you must know their process ID value. So that's the way in which a process can schedule other processes. So it's a normal, it's the standard solution for that.
All right, okay. Thank you.
Okay. So the process ID is the universal way of identifying a process. So anytime a process has to interact with other processes, in particular using events or signals, you always have to know to build your own table with the process to interact with, because the only way to send a signal is to identify the destination process with using the process ID.
All right. Okay.
But you know that there are system calls to know the process ID, in particular, any further process just after forking knows the process ID of the son. So look inside the slides and you will know all the, okay? Let's go inside the problem that is called the dining philosophers. Oh, it is a metaphor, of course. It's a short tale that should be funny and amusing in some way, and is the sort of a prototype, or let me say in the right term in English should be the archetype of a problem of depicting what is a deadlock and how to avoid deadlocks. And also another concept that is called starvation or a live lock. So not a deadlock, but a situation in which, in any case, the system, the computation cannot proceed. It was defined by Dijkstra. Dijkstra was a prominent scientist who invented the concept of, defined the idea of semaphore in distributed, in concurrent computing. And we can say that semaphore is the primitive concept that allows us to have operating systems in general. Without Dijkstra's semaphore, we would have no computer working like we know today. So it's a short tale. You can go and browse the window, browse the internet, and asking for dining philosophers problem. And it's really a bit funny in the sense that the idea is that you have a round table with 5 dishes of spaghetti, and that's the original formulation. And the strange 5 guys come and they want to eat spaghetti. Spaghetti are unlimited resources, so they can eat forever. And the idea is that asynchronously and non-deterministically, each philosopher enters the room and wants to pick up 2 forks to eat spaghetti. Well, it's not the normal way we do that, not only spaghetti, of course, and not in the pandemic era, but in any case, the idea is that they pick up a fork. And they eat for a random amount of time, limited time. So after a limited time, they put down both forks so that the side philosopher can pick up the fork. So resources from a computer science point of view are not spaghetti, because they are unlimited, are forks. Forks are resources. If some philosopher picks up 2 forks, like in this case, the right lower corner philosopher picks up 2 forks, the side philosopher cannot pick up the fork, so it waits until the fork is again on the table. This is just an archetype, with not necessarily there are 5. They can be 6, 7, 3, or even 2. I don't know why the number 5, because probably it makes the problem a bit complex and not trivial, but not too much. But in any case, the number of forks is not important. The number of philosophers, I mean, and consequently of forks. Why this is a theoretical problem that is very important? Because it just it's as inside all the concept of what we call deadlocking. Why deadlock? Deadlock is a situation in which this computation, consider that each philosopher is a single process in our terminology, and the forks are something that must be managed by some other process or shared memory or something like that. We will sketch a solution. I want you to sketch a solution on your own paper, on virtual paper, for this in pseudocode. The deadlock is a situation in which, consider, for example, an algorithm in which each philosopher, and is just written here clearly in Wikipedia, picks up the right side fork. But consider the possibility that in some situation, unfortunately, all philosophers picks up their right fork. In this case, each philosopher cannot pick up the left fork because is occupied or already in use by the left side philosopher. In this case, if each philosopher waits for a fork to be free, is a deadlock situation in which they all wait forever because there's no way of making the concurrent algorithm to go on. This is a good representation, logical representation or pictorial representation of the concept of deadlock. Deadlock is a circular situation in which each process depends on the another process in a circular way, no way of proceeding. So we want to avoid deadlock. We must write the concurrent algorithm, those we are sure in advance that no deadlock will occur in any case. So deadlock is not something that happens, it's something to be prevented logically. And this made the Dijkstra the possibility of, when he was a student, he was still a student, he decided to define the concept of semaphore. We will not use the semaphore, but there is another concept that is the starvation or live lock. Live lock as opposite to deadlock. Starvation is a situation in which you're not blocked, so there's no deadlock, but the computation in any case does not go on. Why? For example, suppose that the algorithm is that each philosopher picks up the right fork, but if he sees the left fork occupied, after a while, after a determined given time, to avoid deadlock, he puts down the right fork that he had asked and reserved in advance. So just to prevent deadlocking. But there could be a situation in which all philosophers do that simultaneously with the same cycling time. So if you look at the computation, you will see that each philosopher comes, picks up one fork, the right fork, they wait for a given time, and they put down the right fork. They pick up the right fork again. They don't have the left fork because the left philosopher did the same. So they wait, after a given time, they put down the fork again. This is a limit situation that may in any case occur. It's if all philosophers do the same thing all together, and if they have the same guard time, so after the same time they put down the fork. This is a limit case of what is called the starvation. So a system that is computing but does nothing useful. These are the two situations that may happen in concurrent programming. And to avoid them, we must use some result, some solution scheme. How to do that? If you read the Aula web, you will see that one possibility is to define a system component that is the waiter. The waiter manages all forks. So philosophers cannot directly pick up a fork. They have to ask the waiter. So the manager, this is the normal way, probably the more efficient way of solving if you don't have a shared memory. So if you have processes that must communicate. And now let's try to sketch the situation with a rough scheme as ever. Okay. I've seen that I forgot to, sorry, I didn't start the recording. Terrible.
Oh,
No,
it seems
no, no.
on.
Started.
Yeah.
Okay, it's already on, unfortunately. Was scared of that. Go back and, okay. Let's sketch how to solve this before using pseudocode, just a rough sketch. All right, dining philosopher. The waiter. The waiter process. Oh, let me write. Waiter process. Waiter process is a process. Oh, sorry. Is a process that basically manages a data structure. The data structure is an array with forks. You can write 0 or 1 to say that the fork is in use or is a free. So if the waiter works properly, the waiter interacts with all philosophers. So philosophers are processes who talk with the philosopher. There are, of course, 5 philosophers, so there are 5 processes. Philosopher 0, philosopher 1 until 4. What does the philosopher? The philosopher is the process, very simple, that simply has to, well, to make it very, very simple, the simplest solution is to have 2 pipes. So each philosopher has 2 pipes. I will explain why 2. 2 pipes to talk with the waiter. So there are 5 couples of pipes. One is for asking. And one is for giving back. So the philosopher is a loop, simple loop that asks. What the meaning of asking? Asks 2 forks. In particular, the philosopher asks. The philosopher I asks forks I and I plus 1 module 5. So if the philosopher number 3 asks conventionally the fork in position 3 and 4. Well, 2 and 3 if the index is 0, 4. After asking a fork, this is a blocking communication. So asks the fork. If this communication succeeds, philosopher 0 or philosopher I knows that he has two forks. So eat, in the metaphor, that means if you want to implement, and I want you to implement, to encode this, you delay for a random time. Random, so that each philosopher is different from any other philosopher. And then give back. Yes, the philosopher is over. Nothing else to write. So all the intelligence of the algorithm is in the skill of the waiter. The waiter has to manage all the requests and how. Let's well, we save this. Well, okay, it doesn't matter. Well, I will change that to new waiter. The waiter, remember that the waiter as the manages the fork database. So the waiter is a loop, an endless loop, which accepts two messages, two kind of messages from all pipes. First, it looks for the put down or give back. So accept all give back. That means try to read from all pipes with the give back, possible give back messages, and execute directly. So accept all give back means that you write here for every give back, right here, for example, into the two forks, for example, from 1, you write 0. If 0 means free fork, all give back will produce just updating this table. Then after accepting, probably is a maximum priority to the forks, you accept the ask, but no, not, well, sorry. Accept ask request from the ask pipes, provided that the forks are free. And that's, in that case, you do the opposite changes in the table. Accepting the ask will let the philosopher to proceed and to simulate the eating and keeping the occupied the forks in use. Consider that in both cases, you have to use the select. Why use the select? Because you have to watch all the pipes give back, but to avoiding blocking, you have to satisfy only pipes with messages. And in this case, the guard of the select is a bit more complex, since you have to accept to consider only ask messages, but to exploit ask messages only in case the fork are free. So to take into account only the pipes coming from the numbered philosophers, so that they correspond to free forks. And the loop, this is loop, not loop, is over. So the waiter is a loop with two selects. So this select, each select has 5 pipes, and this one also 5 pipes. 5 because each philosopher has a communication with. So if you want to depict completely, this is the waiter, philosophers P2, P3, and so on. These are the 2 pipes, and these are the 2 pipes. Ask and put down on release. Well, the name was give back. 2 pipes. This is the scheme. It's not complex. The only complex thing to write is the logics of those 2 selects. And this is the solution, the waiter solution. As you can read in Wikipedia, there are all the possible solutions, but using processes, so no shared memory. This is the way of solving this, and being sure that no deadlock can occur. Let me save before I forget this. Okay. In the last 15 minutes, please go back and start working on this. We will proceed in the next week lesson, just having, since it's a complex problem, it's an absolutely complex problem. So please take it. My suggestion is at home, code the previous exercise and upload also the pseudocode for the exercise of tomorrow. But keep in mind also how to solve this. And next time we'll resume this, and you in groups will go on in solving, because it will not be evaluated, but is really, really important. So please go and in the last part of this lesson and work on this.
I have a quick question.
Yeah.
Before that, how do we communicate to the philosopher that he can go, that it's fork are free? Need to write back to the pipe,
Take
or
to the pipe. The pipe is blocking. So if the philosopher asks for forks, but the message asked is not read by the waiter, the philosopher waits.
okay, yes.
Okay.
Yes.
Just work on this. Good, welcome back. So the lesson is over. I hope that you have worked it together, we have discussed it, and I hope also that you you keep in touch each other in groups in which you have met and people you have met. So only thing I have to do to say that watch our web, and as soon as you find the place to which in which upload your solution, please do it. Please do it and share your solution and your proposed solution with other students. Nothing will be evaluated. Okay, thank you very much. Keep in touch. You know that on Saturday, as always, there will be the question and answer meeting if you want to attend. And in any case, you, for any purpose, just call me on Skype. Okay? Thank you. Stop recording. Bye-bye and see you next week.